Hello, this is the Wanxin from University of Luxembourg. In this video, I'm going to talk about the paper titled Empirical Evaluation of Mutation-Based Test Case Prioritization Techniques. This is a journal first paper published at STPR, and this work is a collaboration with Professor Xin Yu from KAIST, Professor Mike Papadakis from University of Luxembourg, and Professor Duan Bae from KAIST. This study is about test case prioritization, diversity-aware mutation analysis, and empirical evaluation using real-world and developer-written test cases. I'm going to talk through each of them one by one. Let me talk about test case prioritization and regression testing first. When we update the software, it is very important to ensure that previously developed and tested software still performs correctly after a change. It is important because a fix for a problem in one area frequently causes a bug in another area. There is one important question like, can we detect potential faults as early as possible? Test case prioritization addresses the question. It aims to prioritize test cases to detect more faults as early as possible. If you look at the example below, you can see that there are 5 faults and 3 test cases, and you can already see that the fault detection information. It shows that test case 1 detects fault 1, and test case 2 detects fault 2 and 3, and test case 3 detects fault 1, 4, and 5. From this fault detection information, you can already see that executing T3 first and followed by T2 is clearly the best ordering of the test cases to detect more faults as early as possible. But this information is known only after we re-execute all the test cases, and this takes too much time, and the idea is, how about using historical information to detect the faults as early as possible? Yes, we can use a surrogate for the fault detection based on the historical information of the test cases, hoping that the early maximization of the surrogate will result in the early maximization of fault detection. The example surrogates include structural coverage such as branch or statement coverage, or you can use the mutant kill information. Considering the coupling effect between mutants and real faults, it makes sense to use the mutant kill information instead of the real fault detection information. However, there is an issue called traditional mutation analysis. To discuss this, let's quickly see a simplified version of the mutation analysis process. It first injects many mutants, that is, artificial faults, into an original program. And then it checks whether a test case can kill the mutants, meaning it is able to detect the difference between the original and the mutants. And then it simply counts the number of mutants killed by a set of test cases or a test suite to measure or assess the effectiveness of detecting faults. The issue comes from the last point. To see why, let's go back to the point where we generate mutants. When we generate mutants, those mutants are basically diverse. However, since we just count the number of killed mutants without considering the diversity of mutants, the mutant diversity is not properly considered in the way of mutation analysis. To address this issue, I and my colleagues proposed a novel concept called mutant distinguishment, which enables diversity-aware mutation analysis. In the definition of mutant distinguishment, 2 mutants are distinguished from each other by their kill patterns. For example, in the example below, each mutant has a unique kill pattern made by the 3 test cases given in the table. Note that No extra information is required other than just the mutant kill information, which was actually required to the traditional mutation analysis. In this example, we can already see that T1 is enough to kill all the mutants. However, the three test cases T1 to 3 are required to distinguish all the mutants from each other. In summary, both traditional and diversity-aware mutation analysis use the same input, which is the mutant kill information, but they are different in the way of using the same information. The traditional mutation analysis used the mutant kill count, while the diversity-aware mutation analysis used the kill patterns. As a result, the mutation score in the traditional mutation analysis is simply the percentage of killed mutants. However, in the diversity-aware mutation analysis, the mutation score can be represented by percentage of distinguished mutants, which include the notion of kill inside. For more details about diversity-aware mutation analysis, please refer to the TSE paper titled A Theoretical and Empirical Study of Diversity-Aware Mutation Analysis, Mutation Adequacy Criteria. In this paper, we theoretically proved that the new diversity-aware mutation adequacy criterion subsumes the traditional kill-only criteria. Also, we empirically show that diversity-aware criterion increases the fault detection effectiveness around 8 times compared to the traditional criterion. Of course, it is not free. It also increases the test suite size around 3 times. However, it is very true that the increasement in fault detection effectiveness is clearly much more than the increasement of test suite size. When it comes to the mutation-based test case prioritization, we can now consider two objectives. One is from the traditional one, which is just counting the killed mutants and try to kill more mutants as early as possible. On the other hand, we can also consider the B criterion, which tries to distinguish more mutants as early as possible. On the other hand, we can consider different approaches, like the greedy approach, which is the well-known prioritization approach that iteratively selects a test case, maximizes additional killed mutants or additional distinguished mutants, depending on the criterion or depending on the objective we are considering. We can also consider some kind of hybrid approach, the hybrid between K and D. It can iteratively select a test case that maximizes the weighted sum of additionally killed and distinguished mutants. Instead of iteratively selecting test cases one by one, we can also optimize on ordering of test cases as a whole using optimization algorithms. However, due to the 20-minute time limit for this presentation, I'm not going to provide the details for this multi-objective optimization approaches. If you are interested in, please refer to the paper. In summary, this paper considers 7 different prioritization techniques. The first 3 are already presented in the previous slide. And then MOK, MOD, those are the multi-objective based approaches which are not the focus of this presentation. At the end, we have additionally introduced 2 techniques which are R&D and SCV. R&D is simply random ordering of the test cases. This is kind of the baseline of every techniques. The last one, SCV, is a statement coverage-based test case prioritization technique. And it is basically greedy approach, but it's not using the mutant kill information, it's using the statement coverage information. This is of course another baseline for the mutation-based test case prioritization techniques. These 5 research questions guide the experiments. Again, I'm going to focus on the first 3 because The last two are mainly related to the multi-objective optimization techniques. The first research question is how the mutation-based prioritization techniques compare with the random and coverage-based techniques in terms of their prioritization effectiveness. RQ2 is about what is the superior mutation-based technique, and RQ3 is about what is the effect of using different weights for the hybrid technique. To perform the mutation-based empirical evaluation, we used a total 352 real faults from 5 real-world Java programs provided by Defect4J at the time. And each fault is given by independent pair of faulty and fixed versions. And for each fault, Defect4J also provides relevant developer-written test cases that touch the modified classes between the faulty and fixed versions. We also used major mutation analysis tool to perform the mutation analysis and collect the mutant kill information. In the table below, we can see the quantitative summary of the programs, faults, test cases, and mutants used in the experiments. In this table, DT represents the number of fault detecting test cases, and AM, KM, DM represents the number of all mutants, killed mutants by the test cases, and distinguished mutants by the test cases respectively. To measure the prioritization effectiveness, we used APFD, average percentage of faults detected, which is the most widely used metric to measure the effectiveness of prioritization. We also performed the statistical analysis, and to do this, for each fault we repeat 100 times of each technique to generate 100 APFD values per technique. And then we perform band-hitting U-test to determine whether a pair of techniques are statistically different in their prioritization effectiveness or not. We also measure Verga and Delaunay's effective size measure to represent the effective size of the effectiveness difference in terms of the prioritization. This is the first result for RQ1, specifically for the comparison between mutation-based and random techniques. The column pairs show the two compared techniques, and the column superiority shows the number of cases where the technique A is statistically superior, equal, or inferior to B. Recall that we have total 352 cases from the isolated faults. And the column effect size provides the average effect size value to present how much one technique outperforms the other in average. Overall, the mutation-based technique are statistically superior than or equal to random for 95% of all subject faults. The average effect size value is around 0.85, which means that the difference between mutation-based and random are very large. The result compared to the statement coverage-based technique is almost the same as previous one. Overall, the mutation-based test case prioritization techniques are statistically superior than or equal to coverage-based for around 83% of all subject faults. The average effect size value is around 0.77, which means that the effectiveness difference between the mutation-based and coverage-based are also very large. The comparison results between mutation-based techniques are different from the previous one. Here, we cannot say that one technique is clearly superior than the other. For example, comparing GRK and GRD, GRK is more effective at around 60% of all faults, which means 214 faults among 352, whereas GRD is more effective at 88 faults among 352, which is around 55% of all faults. As a result, the answer to the RQ2 is that there is no single superior mutation-based test case prioritization technique. This shows the result for RQ3, which is about the effect of changing weight values in hybrid technique between kill and distinguish. The figure shows the result. The x-axis is the weight value and y-axis the APFD. Interestingly, all the subject programs show the same result, which is the highest APFD appears when the weight value is between 0 and 1, neither 0 nor 1. From this, we can say that the combination of GRK and GRD increases the prioritization effectiveness. Before concluding the experiment, we investigated why the superiority between GRK and GRD varies a lot for different faults. Specifically, to visualize how a set of test cases kills and distinguishes the mutants and where the fault detection test cases are, we propose a graphical representation called mutant distinguishment graph, in short, MDG. In this graph, a node is a set of undistinguished mutants, and directed edge from NX to NY is a set of test cases that distinguish mutants in the node NY from the mutants in node NX. The thickness of an edge represents the percentage of fault detection test cases. Assume that we have mutants kill and fault detection information as shown in the left table. It shows that T1 kills all mutants, T2 kills M3 and M4, and T3 kills M2 and M4. We already know that T3 is the fault detecting test case among the 3 test cases. This information is visualized using the MDG shown in the right. We have a root node, and T1 distinguishes all the other mutants from the root, as T1 is the killing test case that kills all the mutants. We can also see that T3 distinguishes M2 from M1 and M4 from M3, and the thickness of these edges are thicker than the others because T3 is the fault detecting test case. Using an MDG, we can explain when the test case prioritization effectiveness of GRK is better than that of GRD or vice versa. When there is at least one thick edge from the root, GRK is more likely to be effective than GRD. This is because GRK gives the test cases in the edges from the root high priorities to kill more mutants as early as possible. For example, the left MDG shows a typical case where GRK outperforms GRD. On the other hand, the right graph shows the case where GRD outperforms GRK. In conclusion, we applied diversity-aware mutation adequacy criterion in mutation-based test case prioritization. We found that the combination of traditional and the new diversity-aware mutation criteria increases the prioritization effectiveness. There is no single superior technique for all subject faults, but we proposed a visual representation of both mutant kill and fault detection information at the same time. Thank you for watching this video, and please feel free to contact me if you have any questions or ideas to discuss together. Thank you.